And the second speaker is Abdelrahman. He is a front-end engineer at Robusta Studio, the creator of vue-validate, and an open source contributor based in Cairo, Egypt. Hello,
Hi everyone.
how is the weather there?
It's pretty hot, I guess.
Oh, that's so nice. It's so cold here in Sweden. Well, today, I know that you are not only going to introduce us new ways to share functionality across components using the composition API, but also talk about how Vue adaptive utils to use it to develop apps that can adapt the user experience to their own devices. So that is definitely a very good, like, user-focused talk, I assume.
Yeah, it is because we always currently we mostly adapt to the screen sizes, which is called responsive web applications. But there are many hardware aspects for the user device, and giving the users better experience using other hardware resources like CPU and others that you will see in the talk will allow you to serve more users better. So this is mostly an experimental talk. It's not really. I mean, you would find some difficulty finding practical applications for this in your day-to-day life, but hopefully we'll see how it goes.
Well, as developers, we do sure like to experiment. So your talk is going to be is a recorded talk. So I welcome you all to the recorded talk, Adaptive Vue.js Apps with the Composition API, and we will come back with questions later on. See you soon.
Hello everyone, I'm very excited to be here today. I will be talking about adaptive components with the Vue.js Composition API. So first, a little bit about me. I am Abdelrahman Awad, a front-end engineer at Robusta Studio. I am from Egypt. I am an open source contributor and I am the creator of vue-validate. I usually blog about Vue.js and other front-end stuff at my blog, logarithm.com. You can also follow me on Twitter with my handle at logarithm. So, let's get started. The word adapt. So, let's talk about another word first so we can better understand this one. The word responsive usually means web applications that respond to the screen size. So, in other words, it works well on mobile phones and 4K screens, and what's in between. For adaptive web applications, it's still the same thing, but for other device specifications than just the screen width. The screen size is just one factor of the equation. We also have hardware specifications like CPU, memory, and others. So, adaptive web applications are web applications that respond to the device's hardware capabilities. We will take a quick look on what resources we can adapt to, but in a minute. So, what is our agenda? We need to get the idea of adapting to low-end devices and high-end devices and what's in between them, because the difference between adaptive and just responsive web application is that responsive web applications or screen sizes in general is no matter how diverse they are still very finite. You can have very finite number of screen sizes that you can target and that would be it. But with hardware specifications or hardware capabilities, it's a very big spectrum. The spectrum spans a very wide range of diverse and inconsistent configurations across user devices. You can have very powerful mobile phones, you can have very weak mobile phones, you can have PCs with a lot of memory but hardly any processing power, and you can have the exact opposite. You have a processing power beast but you hardly have any memory to work with. So because of this, we have a very hard and diverse specifications that we can adapt to, and we can target only just small portions of that spectrum. However, the idea is still the same as screen sizes. You adapt to a low end and a high end of devices, and what's in between, of course. It is also a form of progressive enhancement and graceful degradation. So unlike screen width or screen size in general, it's not a progressive enhancement or a graceful degradation, it's just the way the device is. But for hardware capabilities, it's not exactly the same. So devices may have a very good processing power, very high processing power, very high memory, and they might have the exact opposite, a low memory and low processing power. So depending on which you want to target by default, maybe you want to target high-end devices by default, you are building for them, and you are providing fallbacks for low-end devices. So this is graceful degradation. So you are cutting back some features, you are cutting back some stuff in your application. So that's graceful degradation. And we have progressive enhancement. So you target low-end devices. This is a default experience. And if you happen to detect that the user have a high-end device, you give them more. So it's the same thing mostly, but it depends on how you think and which end of devices you are targeting by default. So this brings us to another idea, which is setting hardware budgets for our components or our applications in general. So just like video games, if I am sure many of you play video games, so video games usually have system requirements, especially the ones on PC. So system requirements is a sheet of specifications that your device should meet to be able to experience the game at a certain level. So minimum system requirements, for example, allow you to just play the game. It's playable, but it's not the experience that the developers of the game wanted for you. You won't have all the nice effects that they spend a lot of time building for you, and you won't have a very pleasant experience. On the other hand, if your device meets the recommended requirements, or maybe even the maximum requirements, then you will experience the game at exactly the way they intended for you. So overall, it's not just playable, it's pleasant, and it is full. So this is our agenda. We will check how can we achieve that by viewing a lot of snippets and demos that showcases these ideas in a way. So let's start by reviewing what kind of resources are we planning to adapt to. First, we have the CPU. So devices can have a multi-core CPU, they can have a single-core CPU, they might have a very fast CPU, and they might have a very slow CPU. Its frequency, base clock, and other factors. The user also might have we can adapt to the memory. So they might have high memory or low memory. It's just the RAM size. So it's nothing really complex like the CPU. We can also adapt to the power level of the device, because currently I think all the devices are generally battery powered by today. It wasn't that way from 5 years ago maybe, or even more, but certainly the world has become more mobile since then. Everyone is moving around with phones, everyone is now moving around, if not phones, maybe laptops, and of course both. So you no longer have just desktops to worry about. You pretty much have to worry about mobile devices, specifically battery powered devices, more than desktops or PCs, which I mean wired devices, in other words. We also have network. So network, the entire world is connected to the internet at the moment, but they are not equal. Some areas it's faster, some areas it's much slower. So you want to be very careful how to, and if you can provide a pleasant experience for both ends of users. So let's start with the CPU. So first, I am using a little library I wrote called Vue Adaptive Utils. It exposes composition function APIs for Vue.js that you can use to adapt to these APIs in a vue-ish way. So at least in a composition API way, to be more exact. So for the CPU, we have a function called use hardware concurrency. This function gives us access to something called the concurrency value. The concurrency value tells us how much cores or logical CPUs does the CPU have. So in other words, how much concurrent work can the CPU handle at the exact same time. What can we do with this information? Well, we can do quite a few things. We can use it as an indication of the user's device's processing power. So just an indicator for the processing power. If they have more cores, then it's very likely they have a very high-end CPU. And if they have very low core count or concurrency count, well, then it's very likely they have a low-end CPU. So we can just disable some features like animations, JavaScript, if the core count isn't satisfactory to us. So in this snippet, I'm just checking if the concurrency value is less than 2, and if it is, we are just rendering a div with a conditional class. If it's less than 2, we will render disable animations class. The disable animations class will make sure no animation is being rendered in our application, or at least in this container. For example, maybe we can unset all the animations. Maybe we can also unset the transition value, the transition time, to maybe 0 or whatever. So we disable some stuff in CSS. We can also do it in JavaScript. If you have animation loops that's done with JavaScript, you can disable it as well in the exact same way. Here I'm using the render function API to be able to pack the entire snippets into just one example, so I don't have HTML and JavaScript around. It's still the same idea. You can do pretty much the same in the template. So what else can we do with the concurrency value? Well, by extension from the previous snippet, we can conditionally render expensive or cheaper components depending on the user's CPU concurrency level. For example, we can, if they have here in this example, if they have less than 4 core count or equal to it, we will render a cheap fallback. Otherwise, we will give them the default or the full or the expensive component experience. We will render totally different component that's more expensive CPU-wise. Maybe it has more animations, maybe it has more JavaScript background processors running, maybe it has, so it does more, in other words. Another exciting example is that we can split the workload across some number of web workers. So JavaScript in general is single-threaded, and while we have asynchronous APIs that we usually invoke, calling by like fetch, maybe set timeout and promises, but they are still being executed on a single thread. So we are not doing true concurrency here. So true concurrency in JavaScript or in the browser can be done using web workers. And in this example, we are actively using the concurrency value. We are not just using it as a measure for the user's processing power. We are actively using the number to spawn as many as web workers as we can, guaranteeing we use the CPU processing power to its full extent, which is what happens in this example. We are just spawning as many web workers as the concurrency level value is. So we just utilize the full power of the CPU. I have a demo for this and it's very exciting. So in this demo, I have right here a simple simulator that allows you to test multiple concurrency values, but we will start with the automatically detected one, which is 12 in my case. So this example, I can select an image and this image will have its colors inverted on the other side. So we just render the image and its colors will be inverted right here. So it took some time, so it took around 12 seconds, slightly less, but that's the total time. The time, of course, isn't very accurate because it doesn't take into account the overhead of spawning web workers and communicating between the main thread for sending the image data to them and grabbing the data back from them. So it's not very accurate, but still can be used as a good indication of the speed up that you will potentially get. So if we change the number to something like 1, so we are just running the entire thing on just one web worker, and we run the exact same example, it should take longer, so it's a lot slower. So what happens here in the background is that we slice the images just like a pizza. So each worker gets its own slice of the pizza and each can consume or process its own slice. So they can finish. The more we have, you have the likely you are to finish faster. Which is the case here. We have slightly less than 19 seconds. So we have quite like maybe 7 seconds difference, which is, while not very impressive, it's still quite a lot. Like I said, there is a overhead related to spawning workers and initializing them and sending them data and grabbing the data back. So this isn't actually the speed up you would get normally from having like 12 the factor, of course. I think the difference will be much greater, but you can choose much larger images. So this image have about 6 million pixels, and you can certainly get much bigger images, and these images would definitely show you the speed up that you would get by utilizing more cores. Anyways, for memory, we have a function called useMemoryStatus, which reports a lot of useful properties like the device memory, which is the device RAM size in gigabytes. It has a maximum of 8 gigabytes, so it won't report anything more than 8 gigabytes. So if you get 8, then it's pretty much a very high-end device. We also have some stuff that are Chrome only, like related to the heap size for the JavaScript, so you can get the allocated size, the total size you currently can use, and the current one you are actually using. This can be useful if you are building an application that's meant to work in a Chrome environment only, maybe an Electron app, for example, which can be very useful if you are doing a lot of memory allocations and you want to be very conscious about your memory usage. So what can we do with this information? Well, it's basically the same idea as the CPU. We can selectively load smaller or larger resources like videos, images, and textures based on the memory size. So if the user have a higher memory, we can load more expensive resources. And if they have low memory, we should load less taxing resources. In this example, we have like an intro banner maybe, and this banner component checks the device's memory. If it has more than 4 gigabytes, it will load a video. Otherwise, it will load a still image. So it is more conscious of the user's memory and it adapts to it by rendering less or more expensive resources. It pretty much is the same idea. So while we don't have a lot of use cases for this, they are pretty much the same idea. You selectively load different components based on their expense on the user's memory. So in this example, I have an e-commerce page for maybe a furniture website that sells furniture. So it will be very useful if the user have access to a 3D model just like this one. So they can see the thing they are buying and they can get a pretty good idea on the overall design of it. So they won't miss anything. So what happens here is I automatically detect that the user has 8 gigabytes, so I give them a 3D model. Of course, they have more than 8 gigabytes, and in my case, I have about 16, but still we are limited to 8 max with this API. If I change it to something less, I have built a simulator here that you can simulate less capable devices, so maybe 2 gigabytes. It will fall back to just a simple gallery that you see in almost all e-commerce or applications that sell products. So it's just a simple gallery. The user can select the image and they can view the image they selected. It's nothing fancy. But once you go back to more than 4 gigabytes, you get the 3D model experience. So in other words, we adapt it to the user's memory size, and if they have a lot of memory, we give them a pretty good experience, the full experience. We give them something that's really cool, but we know it's a little bit demanding. So for users with low-end devices, we give them something more expected or something that's suitable. That's what's called graceful degradation. We don't ruin their experience. We give them something that's suitable to their device's capabilities and still not interrupt their experience. For high-end devices, you can do something extra here and give the users a full control over what they want to see. Maybe they want to see the images, maybe they want to see the 3D model. So you can toggle between the two, giving user control if they have a lot of memory. Otherwise, you should just render a simple gallery, which won't deny the user their experience. They can still see the product, and it's pretty much in every other website. So you didn't punish them for having a low memory device. In fact, you give them exactly what they would expect, and for high-end devices, you give them something extra. So for power, it's slightly different. We have a lot of information that we can use, not just the device memory. So we can check the current charge level of the device, its current battery level. Starts from 0, ends at 1. It's a percentage based. We can also check if it's currently charging or not, if it's plugged in or not. And we can also know how much time does it need to be fully charged, or how much time does it need to be fully discharged. So, which depends, of course, if the user plugged in their device or not, but still they are estimations, so they are not accurate. This API only works in Chrome though, so don't try it on iOS or anything like this. It just will work on Chrome and Chrome Android. So what can we do with this information? We can pretty much implement low or high power modes for our components. So think what happens when your mobile phone goes below 20%. Whether you're Android or iPhone, they do pretty much the same thing. They prompt you to activate power saver mode or low power mode. So what happens when you do that? Well, some animations get disabled, maybe some colors change, maybe the screen dims a little bit. Some background applications certainly get stopped, so they won't consume a lot of battery. And pretty much it. Maybe your bandwidth gets limited, so it's not as fast using the internet as it would with a higher charge level. It depends on your device and what it does once it goes below 20% or whatever threshold it might have. Still, it's the same idea. We have a low power mode and a high or default power mode for your operation. So in this example, we have a component here that does something similar to what we had in the CPU snippets. It checks the current power value, and if it has less than 20%, it will render something that's doing less. It's doing less animations, it's doing less background tasks, because you see the power isn't a direct resource we can directly affect. We can only affect it by utilizing other resources. So the more CPU we use, the more battery we drain. The more memory we use, the more battery we drain. The more bandwidth we use or network stuff we do, the more battery we drain, and so on. So by doing more, we drain the battery more indirectly. So still, in this example, I'm just checking if it's below 20%, and if it is, we will render something that we know is definitely cheap. Otherwise, we will give them the default experience or a higher power mode experience, depending on how you look at it. This can be applied to the exact example as the memory. We can load the 3D model if they have more than 20% charge, and maybe we can load the images if they have less. So I have an example here. It only works on Chrome again, and Chrome Android, because this API only works on Chrome for now. So let's check what we have here. Well, we certainly have a lot going on here. We have a few cards that's angled, and they have their colors changing across time, and they have this floating animation going on. So it tilts slightly to face the screen directly, and if I leave it, it will also tilt back to its original position at a much slower rate. Animation is certainly doing a lot of work on our users' devices, whether it's CPU or GPU or whatever, just doing work. And currently I have, of course, a 100% charge level because I won't be present than 20. That would be a little bit risky. So I built a range slider here that you can use to simulate different power levels. So less than 20%, like 10% here, you notice some things completely change. First, the colors are no longer changing, but the cards itself are now have the full range of colors static. It doesn't change. Also, the floating animation has completely stopped, and when I hover on a card, it automatically faces the screen immediately. There is no delay, there is no animation or transition going on. So this is what a low power mode looks like, and if we increase it more than 20%, the cards go back to floating again. So, and if I hover on a card, it faces the screen slightly. If I leave it, it goes back to its with a transition. The colors also are changing again. So this is the default or a high power mode, depending on how. You can reset to the current level anyways and get back to your default. So let's end with the network. The network is a very exciting API because we have a lot of use cases for it, because it is the most relatable API out of these. So what can we do with the network? Well, we can read the effective connection type, which describes how fast the connection is in terms of connection types. Like if it's very fast, it will report it as 4G. If it's slightly slower, 3G, then 2G, then slow 2G, and so on. This can give you pretty much a good idea on how fast the user speed is. So this is very useful. We also have access to the network type. So this tells you how the user is connected to the internet. Are they using an Ethernet cable? Are they connected using a Wi-Fi network? Or are they connected using mobile data? So this can give you a very good idea on how much the user pays for their connection. So here in Egypt, mobile data is very expensive, but Wi-Fi is pretty much decent. So you can maybe use this information to be more conscious about your bandwidth in your applications. We also have an estimation for the downlink and downlink max, which is the actual megabits per second, I think, that the user can handle. We also have is online, which tells you if the user is online or not. We also have offline at, which tells you when is the last time the user went offline. It's a timestamp. Can be useful if you want to display some counters, and maybe you can watch it if it changes, so you can count how many times they went offline. Maybe you can tell how stable their connection is based on this value. We also have a save data Boolean, which tells you if the user has enabled low bandwidth mode, or what you might know better as power saver mode. Data saver mode. Yeah, I got a little bit mixed up. So data saver mode. I think it's very common in Chrome. Not sure about Safari though. Moving on. So what can we do with this information? Well, we can fetch suitable resources based on the network type, like images, videos, whatever, based on the network type. For example, here we are checking if they have 4G, and if they do, we are loading a video. Otherwise, we are loading a high quality image for 3G, and otherwise, as a fallback, we just load a low quality image. So for 2G and below. You might also want to render a solid color instead of for slow 2G connections, because I don't think slow 2G can load any image at all. So you are better off trying to load JavaScript than images. So you can do that as well. You can make certain resources opt-in if the user connection is metered, or if they are paying significantly for their connection. For example, here we have a lazy video component that's aware of the user's connection type. They know how the user is connected to the internet. And if he is connected, or if they are connected using Ethernet or Wi-Fi, then you will render a video. Otherwise, you'll render an image. But we have a trick here. So our image, when the user clicks on it, it will load the video using a simple Boolean here. So this pretty much makes the video opt-in instead of forced to render on their devices. And this will certainly save a lot of bandwidth. Maybe the image has a little play button at the middle, like a thumbnail with a play button, so the user can click on the image and it will be swapped with a video in its place. So this can be very useful. This is a very advanced use case. We can load layouts with reduced bundle size for slow connection. So what this means is that we are utilizing asynchronous components and code splitting depending on the user connection type. So we might have a full layout and a light layout for the user, one that has a lot of kilobytes associated with it, CSS, JS, and images maybe, while the other is a little bit lighter on that end. So we can code split our layouts and load only the one that's more suitable for our users. You can think of it like Facebook and Facebook Lite. So you are loading Facebook when the user connection is 4G, otherwise you load Facebook Lite. So you can do the two applications, or you can combine the both layouts in the same application bundle. And you will only load the bundle you actually need, or the one that the user's connection can handle. So this is very cool. Our example here is a little bit similar to this, but it operates at a much lower level. So we have here a interactive Google map that we can use you can use a map. So yeah, I didn't build an simulator here because we already have a very good one in Chrome DevTools. If I take the connection slower than online is pretty much 4G for my case. So if I take it to 3G, we instead get a static image. Notice how much faster it loaded. So static images are much lighter than the interactive map, of course. It's using the static maps API provided by Google as well. It's using it as a fallback for users with slow connections. Once I go back to 4G, it will get back to being interactive again. So this can be very useful depending on your case. This is implemented at three components. We have an adaptive map component, and we have a static map component, and we have a interactive map component. So the adaptive map component renders either depending on the user's connection. How fast they are. If they are fast, they get the interactive map. Otherwise, they get the static map. Maybe you can do both at the same time, just like we did at the video, and make it opt-in to load the interactive map if the user connection can't handle it. So what are the takeaways from all of this? Well, we should keep both ends of devices in mind, because we aren't just building for high-end and adapting to low-end devices. We might be building for low-end, just like in the CPU case. We're always building for single-threaded application without giving much care of how many cores we can actually use. We are not utilizing the full power of the CPU in most of our applications. We should also mix and build hybrid adaptive components by utilizing all of these APIs together. You shouldn't just adapt to CPU in isolation or memory in isolation. You should mix and build hybrid components together at the exact same time. So this brings us to the last point, which is we can assign budgets, hardware budgets, to our components and eventually our applications. For example, the 3D model component could have its own budget. Maybe it should be only rendered if the user's memory is more than 4 gigabytes, and if their CPU has more than 4 cores, and if their charge level is above 20%, and their connection is fast, so it can render textures faster and stuff like this. So combining all these specifications together, we pretty much got a budget for our component, a budget for it to run. So this is very similar to video games. Now we have come closer to the analogy I used at the beginning. Video games define their own requirements for running multiple experiences for the same exact game. So you can do pretty much the same thing for your web applications. And while this might not seem very practical at the moment, certainly the network adaptations seem to be very practical, but the others might be not so much. But in the future, when we get more APIs, the web applications will become more capable and more demanding as a result. And because of this, we should be more responsible on how we consume or tax the user's devices. So with great power comes great responsibility. So here are a few resources that you can check out that I used in this talk. And thank you. It was a pleasure presenting to all of you.
This was amazing. I had so many insights from your talk. Thank you so much. Wow. I have a lot of questions for you, though. I will start just shooting them on you. The first one is, does the library support events such as like on-connected change, on-connected for network battery? The CPU is not going to change just out of the blue, but network and battery are two things that can change as you are using the application. Does the library support it?
Yeah, it actually uses all the events that the browser emits for these APIs. For example, the battery actually updates while you are using the device. Also, the connection. You can watch ISO online and always get a value if they are connected currently or not. So you can use them with watch, computed, or whatever things Vue might give you with the composition API.
Nice. Does the library work with native script Vue?
I don't think so because it relies on the web API. I'm not sure how native script works. Maybe we can add a support for it. I'm not sure.
Nice. It's always room for collaboration in open source projects. So,
yeah, definitely.
Sorry. For the features available for Chrome only, does it really work only with Chrome specifically, or did it work with Chromium and the derived browsers from it as well?
Well, it should work on all Chrome-derived browsers. It should work on Edge. It should work on Opera, I think. But some browsers might choose to remove certain APIs because of some privacy concerns. For example, the battery API was actually supported in Firefox, and they decided to remove it because they thought it was giving too much information to the web application. So you should try and test if a certain browser definitely supports it or not. Some browsers might support it partially. For example, the network API might not be fully supported. So, for example, the downlink and downlink max, they won't work on Firefox. They only work on Chrome. So you should always check what you are going to use and maybe pick the lowest dominator in your whatever you're going to use from these APIs.
Yeah, the privacy of the user, of course, needs to be considered, and the developer that is using the library should be aware of being ethical when using it and how to use it.
Yeah, definitely. You can use the CPU function, for example, to check how many concurrent values they have, and if they have a lot, maybe you mine some Bitcoin on their devices. So
don't give people ideas. What are you doing?
Yeah, don't
People
do that,
do not
everyone. I
hear
was
that.
just joking.
Don't do that.
Yeah, don't do that.
Another question, how practical adapting to user devices are at the moment, because we are so like focused on deadlines usually on a daily basis. So how easy it is to do that?
Well, it certainly takes a lot of effort because providing two different experiences, or even more, because we have a spectrum of devices. We just don't have 4 gigabytes or 8 gigabytes of RAM. We have from 1 to 32, maybe even more. So this is always a problem. So it means there is always a lot of effort involved when you are providing different experiences for each device's capabilities. But I would say that if your job doesn't allow you to do such fine tuning and specific things, I think you should maybe be mindful of that and just don't do it at the moment. But just like how responsive web applications in like 10 years ago, we didn't have to optimize for mobile, right? We didn't have to make responsive web applications. But as the time passed, we now have to. You can't actually ship a web application without it being responsive. So maybe in the future we would have to actually um, be adaptive to the user's devices as more capabilities and as more stuff we are able to do in the browser. So at the moment, maybe not very practical, but I would say some users will definitely appreciate the time and effort you put.
Yes, I can see that. And we are coming with new and smaller devices as well, with more limited hardware. So it's good to get to that insight and experience from now. Thank you very, very much for your talk. It was super insightful. We're going to go for a little, like a few seconds break and come back with the next talk.
Bye, everyone.